Welcome to the Journey Shake Chem. I am so excited. I can't tell you how excited I am. We get to start solutions today. Topic 14. Well, you do the 2 warm-up questions to the best of your ability, and then we will discuss them. You might want to take a look at your penguin sheet, and I'll see you in a moment. It's very important that you review the penguin sheet because we are going to be talking about the various things that are on the penguin sheet, the electrolytes, and you must know your 6 strong acids. And we are revisiting this information, not just in this topic, but the next topic and the topic after that. So the sooner you learn it, the better off you're going to be. Well, number 1 asks us to determine if a substance is a weak, strong, or non-electrolyte. And HOH is just water, and water is a non-electrolyte as far as we know up to this point. And the second one is CH3OH. Now, you might have been caught in this trick. It is not a base. That OH is not a hydroxide. A base is a metal with hydroxide, and carbon is not a metal. Therefore, this is a non-electrolyte. Also, NaOH is a base because it is a metal, an alkali metal, and hydroxide. It is one of the strong bases. And then we have N2O3, that is an acid anhydride. It is a non-electrolyte. Electrolytes are only 3 categories: acids, bases, and salts. Number 2 asks to distinguish between weak, strong, and non-electrolytes. Strong electrolytes, if you recall, we had the light bulb and it had a big, strong light coming out of that light bulb for strong electrolytes because we have 100% dissociation into ions, which allows the current to flow through. We have to have moving electrons for the current to flow through. Weak electrolytes are very weak because they only make a small amount of particles and therefore not much of the current is conducted through it. And non-electrolytes, there's just no light at all. So they do not conduct any electricity. Conduction is a very important characteristic in chemistry. And that's number 1 and 2. Well, today we're talking about solutions. And solutions are all around us. The biggest kinds of solutions we have are the ones where we find fish in the ocean, and all of the waterways are solutions. And we live in a big solution of the air. The atmosphere is one big, gigantic solution. And tomorrow we'll discuss more specifically about different kinds of solutions. Now, we know that solutions are composed of 2 different parts, the solute and the solvent. The solute, and we have had these terms before, is in lesser quantity. It is the one being dissolved. Solvent is in larger quantity, normally, and it is one that is doing the dissolving. For example, if I make some Kool-Aid, well, the Kool-Aid is my solute, and the water is my solvent. And now you need to make sure that you have the terms, the very first worksheet that goes with this topic, and we're going to talk about some of the terms and the various formulas on that worksheet. In this topic, we are going to talk about these 4 different types of problems. The first type of problem is a molarity problem. And molarity is a capital M, and that stands for the moles of solute per 1 liter of solution. And molality is a little m. And the little m is moles of solute per 1 kilogram of solvent. And it's important to notice the difference between these two. One is per liter of solution and one is per kilogram of solvent. And we are going to use molality extensively in the next topic. So we're introducing it now so we learn how to work problems with molality. Well, there's an example problem of molarity on the very first worksheet A. And we are given 22.5 grams of potassium nitrate. 22.5 grams of potassium nitrate. Now, you are always given words and you have to change them to formula. So we're constantly doing more practice on nomenclature. Well, to do molarity, I need to get the number of moles. And therefore, I'm going to change these grams to moles. And 1 mole of potassium nitrate, I look on the periodic chart and I add up the values. Well, potassium is 39.1 AMU and nitrogen is 14.0 and 3 oxygens is 3 times 16.0. And again, I write them over. 39.1, 14.0, and 48.0. And when I add them all up, I get 101.1 grams per mole for potassium nitrate. And therefore, I have 101.1 grams of potassium nitrate. And when I divide this number, as you can see, you come out with 0.2225 moles of the potassium nitrate. Then to do molarity, I need to divide it by the volume of the solution in liters. And I'm given the volume of the solution is 700 centimeters cubed. Well, 1 centimeter cubed is equal to 1 milliliter. And therefore, if I have 700 milliliters, then I just change that to liters. And then when I do this work, I get 0.3178. I look back to my original problem, and I want 3 significant digits. And therefore, the 8 rounds to 7 up, and I get 7 up. I get 0.318 molar, capital M, of the potassium nitrate solution. And that's how you do molarity. The next problem we want to talk about is molality. However, before I go on, both molarity and molality, if I'm given a value, for example, if I'm given 2.5 molal, I immediately rewrite this to show that it is 2.5 moles in 1 kilogram. And when I put it in this form, then I'm ready to use it if I was changing it. For example, if I wanted to know the number of moles there were in 1/4 of a kilogram, or 250 grams, then I would just cross multiply, get my moles, and change my moles back to grams. And the same process would be true if I had 5.0 molar of a compound. I would write that again, 5 moles in 1 liter. And from there, then I would say, well, how many moles would that be for 1/4 of a liter? Then I cross multiply to get my moles and then change my moles to grams if I'm making a solution of a specific concentration. These are concentration types of units, molarity and molality. And there are problems on tonight's assignment that you will need to be able to manipulate these equations in this way. So that gives me just a little bit of information about how to handle these numbers. And it seems very simplistic to write that out again, but it has been very, very helpful for students. So I suggest that you try that. So now we have a molality problem. Well, we have 49.5 grams of potassium hydroxide. Again, I'm practicing my nomenclature. Well, I want molality. And molality is moles of solute per kilogram of solvent. So again, I'm changing my grams of my solute to moles. And 1 mole of potassium hydroxide, I need to add up the AMU. Well, potassium is 39.1, oxygen is 16.0, and hydrogen is 1. And when I add up all these numbers, I get 56.1 grams per mole, or AMU, or U. And when I use it as a conversion factor, then I have to put my 56.1 grams in the bottom. And this solves for moles. And I get 0.8823 moles of the potassium hydroxide. Then to get molality, I'm going to divide it by the kilograms of solvent. And in this problem, I'm given 650 grams. And I'm going to change it to kilograms. And there are 1,000 grams in 1 kilogram. And therefore, when I do this division, I'm going to get 1.3573. I look back to my original problem to see the least number of significant digits as given in the problem, and that would be 2. And therefore, I will get 1.4 little m molal of potassium hydroxide. We'll have lots of practice with these problems, so don't be too worried. Try to follow the example problems, and you'll be fine. Finally, we have one more thing to talk about, and that's weight percent, and I'll be right back. Finally, we need to discuss weight percent. Well, weight percent is the mass of the component divided by the total mass. And the problem given to you on the worksheet where you have an example problem is that you have 0.5 moles of potassium sulfate. And we need to change our moles to grams because we have massive component here that we are looking for. And 1 mole of potassium sulfate has an overall mass of 174.3 grams of potassium sulfate. I add up the AMUs for this and get the formula mass. And then I find that I have 87.15 grams of the potassium sulfate. Now I also have 850 milliliters. And for water, 1 milliliter is equal to 1 gram. And therefore, it is a direct conversion there. And so I have 850 grams of water as well. And when I add them together, I get 937.15 total mass. Then I take my 87.15, divide it by the total, times 100. And in this case, I get 9.3% because we take percents to the tenths place of the solute. Now we have the 2 parts, the solute and the solvent, and therefore subtracting this from 100, and I will get 90.7% of the solvent. Now there's one other type of problem to do weight percent, and where we are given molality. Bye. If I'm given molality, by definition, let's say that I have 1.8 molal of sodium chloride. Well, immediately I know that that is 1.8 moles of my sodium chloride for 1 kilogram of solvent. By definition, that is what molality means. And therefore, I'm going to change my 1.8 moles of sodium chloride to grams because weight percent is based on weight, which would be mass. Well, 1 mole of sodium chloride has a mass of 58.5 grams of sodium chloride. And therefore, I have 105.84 grams of my solute. Now, molality means that I also have a kilogram of solvent. Well, 1 kilogram is 1,000 grams. So I just add 1,000 grams of my solvent. And I get a total of 1105.84 total mass. And then to get the weight percent, I take the mass of 105.84, divide by my total mass, and multiply by 100. And when I do this, I get 9.6% of the sodium chloride. And when I subtract that from 100, I will get the mass of the water. And that would be 90.4 would be, percent of the solvent. And it's not even necessary to know what the solvent is. In most cases, it's water for our salts, and that's the universal solvent that we use. However, it doesn't really matter. All I know is that I have a kilogram of solvent. And that's how you do that kind of problem. Well, that was some fun, and thanks for being here. And we'll see you tomorrow.